this platinum compound, which is sold as carboplatin, which is normally known as carboplatin. This carboplatin, it was found that because of the chelating effect of these carboxylate groups, two carboxylate groups, what happens that whereas in the cisplatin, during passage through blood and during the entry into the cell, before the platinum compound can enter into the cell, these chloride ions may dissociate to some extent and may bind indiscriminately to the extracellular targets. But whereas carboplatin, because of its chelating effect, the anionic groups are more strongly bound, so they are not easily replaced. And until and unless it reaches the DNA, it interacts with the DNA, almost this compound remains intact. So carboplatin was found to have much less toxicity than cisplatin. Its action profile is more or less same. That means carboplatin acts on those cancer cells on which cisplatin is also most active. That means the testicular and ovarian cancer, and to some extent head and neck cancer cells. But the toxicity of carboplatin is much less. On the other hand, the activity profile of carboplatin is somewhat lower than cisplatin. That means in terms of anti-cancer activity, in terms of its ability to kill cancer cells, carboplatin is slightly less effective than cisplatin, but it is preferable. Carboplatin is preferable because it is more tolerated by the body. Its toxicity is less. So first compound that was complex, metal complex that was used as anti-cancer agent is cisplatin, and next generation was carboplatin. And gradually more and more platinum compounds came into effect, and one of them is oxaliplatin. Here if you see that all the four coordinate sites of platinum-2 are occupied by chelating agents. Here we have a oxalate group producing two carboxylate ions coordinated. So like here, two carboxylates, here also two carboxylate, but instead of cyclobutane 1,1 dicarboxylic acid, here we have a oxalic acids. That's why it is called oxaliplatin. And instead of ammonia, here we have cyclohexane 1,2 diamine, right? It is a cyclohexane moiety, and 1 and 2, in the 1 and 2 positions there are two amine groups, so it is cyclohexane 1,2 diamine, and this complex is called oxaliplatin. So structurally it is very much similar, two nitrogen donor and two anionic donors, say carboxylate, like here, right? So here oxaliplatin, it is found that again its toxicity is relatively less than cisplatin, but more importantly for oxaliplatin it was found that unlike the cisplatin, this complex was found to have good effect on colon cancer and rectal cancer. So whereas cisplatin or carboplatin is not at all effective against colon cancer and rectal cancer, but oxaliplatin was found to have good effect on killing the cancer cells of colon or rectal cancer. Okay. And
Sir,
another complex here it is. Yes.
sir, can you please tell us the
Yes.
syllabus
Any
of
question?
mid-sem? Sir, can you please tell us the
Whatever
syllabus of mid-sem?
Yes, syllabus is to up to today. Okay, whatever is being up to today, it is the syllabus. Okay.
Okay, sir.
Is it?
Sir, the whole bioinorganic chemistry is in mid-semester, right?
Whole bioinorganic. Yes, right.
Okay, sir.
Okay. So, and then we have another complex called nidaplatin. In nidaplatin, you can see we have two ammonia groups here, and again we have two O- donor, but unlike these two cases, oxaliplatin or carboplatin, where we have two carboxylate groups, here we have one carboxylate group and one alcoholate group, right? So this is called glycolic acid. So from the glycol you are getting glycolic acid. So we have a glycolate anion acting as a bidentate manner. So here we have a carboxylate O-, and here we have alcohol group which is deprotonated. So Nidaplatin. These 4 platinum complexes are most widely used as anti-cancer compounds. So if you are asked about 2 or 3 anti-cancer platinum complexes, you can name these 3 or 4 complexes. Now, beside there are other anti-cancer platinum 2 compounds. So again, this is a platinum 2 compound where you can easily see, like the previous case, here you see there is a carboxylate group and there is an alcoholate group. Here also we have a alcoholate group, right, and we carboxylate group. But this is actually the lactic acid moiety, right? And here the amine groups. Here we have cyclobutane 1,2 dimethylamine. So here CH3NH to CH3NH2 is the methylamine. So to the cyclobutane moiety in the 1 and 2 position, the methylamine groups are attached. So you can say this part is cyclobutane 1,2 dimethylamine, and we have this lactic acid moiety. It is called Lovaplatin, right? And finally, the another platinum 2 complex which is used in anti-cancer chemotherapy is called Spiro Plating. Here we have again the cyclohexane moiety, and unlike the previous case where cyclohexane moiety we have two amine groups directly bound to 1 and 2 position of cyclohexane. Here you find that in 1 position of the cyclohexane there are 2 methylamine groups, CH2NH2, CH2NH2. So cyclohexane 1,1 dimethylamine, and in the anionic groups here are, or rather the anionic group here is 1 sulfate group acting as a monodentate fashion, and 1 water. So sulfate, since it has got 2 minus charge, it satisfied the +2 charge of the platinum. Now the advantage of spiroplatin is because of the presence of water and sulfate, it is more water soluble, right? So spiroplatin has got more water solubility than say carboplatin or oxaliplatin or the nidaplatin. So it is one of the most water soluble platinum anti-cancer compound. So these are I have discussed 1, 2, 3, 4, 5, 6 platinum 2 anti-cancer compound. You must remember at least 2 to 3 of them. Usually you must name cisplatin, carboplatin, and oxaliplatin. That will be better, this 3 complex, and you can also name nidaplatin. But some people may also prefer these compounds, lovaplatin and spiroplatin. Next we go to the next level where instead of platinum 2 compounds that we have used for these 6 complexes, we are using, now people are thinking of using platinum 4 complexes. What is the advantage of platinum 4 complexes, or why people were investigating platinum 4 complexes? It was found that unlike platinum 2, which is more reactive, platinum 4 compounds are relatively more slowly reacting. They are less reactive. What is the advantage of that? Advantage of that is that if you use a platinum 4 compound, sometimes they are called prodrug. What is prodrug? Prodrug means a particular molecule which itself is not drug, but inside the system, after some chemical reaction, it will be converted into the real drug. So real anti-cancer activity belongs to the platinum 2 complex. But if you inject or induct as such platinum 2 from the beginning, what will happen? Because of the high reactivity of the platinum 2 complexes, many of the platinum 2 molecules may get indiscriminately bound to other parts of the body, particularly the blood material and also tissue materials, etc., before it reaches the cancer cell. So that means the effective concentration of the drug molecule at the cancer cell is relatively lower when you use platinum 2 complex, because some platinum 2 complex are lost in the path by binding to the indiscriminately to the other molecules inside in the blood and other cells. Platinum 4 complexes, because they are less reactive, so they will bind or they will react more slowly. As a result of there is a chance that more amount of platinum 4 complexes will reach the cancerous cells. Now, once inside the cancerous cells, in the form of platinum 4, cancer cells are what is called hypoxic cells. Cancer cells are hypoxic. That means they have got a reducing atmosphere, right? Hypoxic means lower amount of oxygen. Lower amount of oxygen means a reducing environment. So since cancer cells are rapidly growing, their metabolic activity is very high. As a result of that, lots of electrons are produced and oxygen is in short supply in cancer cells. So cancer cells has got a reducing environment. They have got excess electrons and they can easily reduce many substances. So once the platinum 4 complex goes inside the cancer cell compared to the normal cell, since the cancer cells has got a reducing atmosphere, so in the normal cells platinum 4 will remain to a long extent as platinum 4, but in the cancer cells platinum 4 will be immediately reduced to platinum 2, and once it is reduced to platinum 2, it becomes more reactive and it begin to bind the DNA molecule. So that means you can target the cancer cells more closely and you can have less toxicity on the other cells. So that's why people are now investigating some platinum 4 complexes which are called prodrug, but their reactivity ultimately when they bind to the DNA, when they show their anti-cancer activity, they are converted to the corresponding platinum 2 compound. Now already 4 or 5 platinum 4 complexes are in use. The first platinum complex that was used as in medicine or as in anti-cancer medicine was this called Eproplatin. This name is coming because it is isopropyl. Epro means isopropyl. So here we have isopropylamine. So instead of ammonia, here we have isopropylamine, and the other platinum 4 is 6 coordinated, unlike platinum 2 which is 4 coordinated, and the other 4 coordinate sites are occupied by 2 hydroxy group and 2 chloride groups. Now once platinum 4 is reduced to platinum 2, then this 2 hydroxy group goes out. So it behaves as if like a cisplatin, 2 amine groups are there and 2 chloride groups are there. So it behaves very similar to that of cisplatin, but it has got much lower toxicity than cisplatin. The another compound is here where we have very similar, except that here we have cyclohexyl 1,2-diamine, like this, cyclohexyl 1,2-diamine. Here we have 4 chloride ions that is coordinate to platinum. It is called Armaplatin. The commercial name is Armaplatin. And again, when you reduce it to platinum 2, this 2 axial chloride goes out and it becomes square planar coordinated with 2 amine groups and 2 chloride groups, and again behaves like a cisplatin. And 2 other compounds are oxoplatin, where we have this part is like the cisplatin, the basal plane, and here we have 2 hydroxy group. And again, on reduction, this to platinum 4 is converted to platinum 2, and you get the cisplatin, and this 2 hydroxy group goes out. And finally, we have satraplatin. Sometimes it is also called GM216. Like Armaplatin is also called tetraplatin. So satraplatin or GM216 is where we have 1 ammonia group, 1 cyclohexyl amine group, 2 chloride ions, and then the axial positions are occupied by acetate. So again, on reduction, this platinum 4 is converted to platinum 2. The axial acetate ion goes out. It becomes a square planar complex whereby 2 chloride ions are there. This ammonia and amine group is there, and finally this chloride ions dissociate and binds to the DNA. Now again, all these different compounds has got different activities again, different type of cancer cell. Particularly, for instance, it is found GM216 or this satraplatin. This is very good against prostate cancer. So for treatment of prostate cancer, this is the preferred agent. Another importance of this GM216 or Cetraplatin is that it is one of the rare platinum compound which has got so much water solubility that you can treat it, you can take it orally. So it is the first platinum complex which can be orally administered, right? So orally fed to the patient, and it is very good for treatment of prostate cancer. So this completes our discussion on the platinum complex, or the list of platinum complex. So we have discussed 1, 2, 3, 4, 5, 6 platinum 2 complexes and 4 platinum 4 complexes, which are used for cancer chemotherapy. Next is, what is the course of action?
Hello, sir.
Of the platinum.
Hello,
Yes.
sir. Sir,
Yes.
do we need to remember the structures? Like if in the exam it is asked to give
Definitely.
example, we need to make the figures.
Definitely.
Okay, sir.
Yes, definitely. Yes. You follow the previous year's questions, you will find they will be asked to name 2 or 3 platinum complexes and write down their structures. Okay.
Okay, sir.
Okay.
Yes, sir. Understood.
And in this year of online classes, it is not at all a difficult thing, difficult proposition. Right. If it is an offline exam, then it was a difficult proposition, no doubt. So we have this. Let us now come to the mode of action of the platinum complexes, particularly the platinum 2 complex. So suppose this is the cisplatin. Now, when it is first administered intravenously, by intravenous drip, it passes through blood, right? Now, in our blood, the chloride concentration is quite large, almost say 100 millimolar, right? So quite large chloride concentration, and because of the extra chloride concentration, the chloride ions cannot go out from the coordination environment, because even if chloride dissociates, there is sufficient chloride in the surrounding. Chloride will immediately get coordinated. So in blood, this chloride ions does not undergo much dissociation. There will be some dissociation, but it may not be very pronounced. But once it goes inside the cell, the chloride concentration is 4 millimolar. So from 100 millimolar, it is coming to the 4 millimolar. So that means chloride concentration is much lower. So when the chloride concentration falls very rapidly inside the cell, then these chloride ions get dissociated, they get replaced by water. So there may be replacement of 1 chloride ion, there may be replacement of 2 chloride ions. And once chloride is replaced by water, then it is found that these platinum complexes, in our DNA, there are 4 bases: A, T, C, G. A for adenine, T for thymine, C for cytosine, and G for guanine. Now, from all lot of experiments, now it has been clearly established that it is the guanine moiety, guanine base, and this nitrogen atom of guanine, which is called N7 nitrogen atom of guanine, through which the platinum complex is bound to the DNA. So, first, this chloride is replaced by water, and this water is again replaced by the guanine from the DNA. And then we have another replacement of water. So suppose we have 2 water molecules, or from here there may be another dissociation of chloride, and another guanine molecule comes. So these 2 guanine molecules are attached in the 1-2 fashion to the platinum complex. So sorry. So this 1-2 fashion, either in this way, it is intra-strand or inter-strand binding may occur, is in these guanine moieties, right? So this is how it is acting. So inside, when it is passing through the blood, this chloride ions is dissociated to a much lesser extent because of the relatively higher concentration of chloride ion in the blood. But once inside the cell, because of the fall of the chloride ion concentration, the chloride ions are replaced by water molecules, and in turn, these water molecules are replaced by guanine. and thus it binds to the DNA. The question is why cisplatin is so much active and transplatin is not so much active. I have told you already, one of the reasons why transplatin is not so much active is it is so much reactive that before it reaches the cancer cell effectively, most of the complexes are destroyed by the extracellular biological molecules, right? And that's why it is so much toxic, and also it cannot bind DNA in this fashion, right? If it transplatin, what it can do, it can only cross-link two DNA molecules or a DNA and a protein molecule, but for transplatin it cannot bind in a 1-2 fashion, right? And as a result, 1-2 or 1-3 fashion. As a result of this, transplatin is not so much effective against DNA binding. The other reason it is found that when platinum complexes bind to DNA and it damages the DNA, and as a result of this, replication of DNA is stopped, then in our body there are certain DNA repair enzymes. That means those are sometimes are something like the police of the DNA. They try to find out where the DNA is damaged. They look out for the DNA damage and they repair the damaged DNA. So in body has got inbuilt certain defense mechanisms called DNA repair enzymes through which it can repair the DNA. Now it is found that if transplatin damages the DNA repair enzymes can easily detect it and easily repair it. Whereas for cisplatin, it is found that once cisplatin binds to DNA and it distorts the DNA, then there is another group of proteins in our body which is called high mobility group protein, HMGP, high mobility group protein. Those high mobility group proteins come and they actually surrounds the platinum bound DNA and protects them from the investigation of the DNA repair enzyme. So as if some shroud or some cloud is coming to the platinum DNA near the platinated DNA, and it is covering the platinated DNA in such a way that the DNA repair enzymes cannot detect easily the damaged DNA and cannot repair it. That's why the cisplatin is so much active, but transplatin is not at all active. So this completes our discussion on the platinum complexes and their application for cancer chemotherapy and how they bind to the DNA. And next we shall go to some other metal complexes. These are less important than platinum, but gradually they are coming to be very much important in terms of treatment protocol. Why? One of the newer variety of anti-cancer compounds are some ruthenium compounds. The ruthenium is actually a congener of iron. So if you look at the periodic table, in the same group where iron is there is iron, ruthenium, and osmium in the periodic table. If we can go back to some extent. So you see here, iron, ruthenium, and osmium. So iron, ruthenium, osmium belongs to the same group. Now I have already told you iron is an essential element, and in our body there is a homeostasis mechanism for iron. That means our body knows how to tackle iron and how to tackle excess iron if the iron is in excess. So ruthenium the theory is that ruthenium being congener of iron, ruthenium can follow similar homeostasis mechanism as that of iron. So that means ruthenium toxicity will be less because ruthenium will follow the same homeostasis path as that of iron. And as a result of this, body can tackle ruthenium in a far better way than it can tackle platinum. So ruthenium complexes are expected to be much less toxic than the platinum complex, and it has been found really it is the case. That means the ruthenium anti-cancer compound shows much less toxicity compared to the platinum anti-cancer complexes, and you can remember these three or these two ruthenium complexes will be sufficient. One is called, the commercial name is called NAMI-A, where ruthenium is in the 3 oxidation state. In fact, in all these complexes, ruthenium is in the 3 oxidation state. In the basal plane, we have 4 chloride ions. And the axial position, here we have one dimethyl sulfoxide group and another imidazole group. You know, in our body there is a very important amino acid called histidine, which has got a this imidazole group. So ruthenium is coordinated by 4 chloride ion, one imidazole, and one sulfoxide ion. And because ruthenium 3, so coordination of 3 chloride makes it -1 charge, and so in the outside there is a cation which is called imidazolinium cation. This nitrogen is protonated, creating a positive charge. So this is called NAMI-A, and very similar to NAMI-A we have Kp418, exactly identical, except this dimethyl sulfoxide has been replaced by another imidazole. So these two are very closely related. Only thing is that the axial position, one of the sulfoxides here is replaced by another imidazole. And another very closely related compound is this compound. So again you will see RuCl4 moiety in the basal plane. In the axial position, we have again a benz imidazole type thing, but it is not imidazole, because you see in imidazole 2 nitrogen atoms are in the 1,3 position, 1, 2, 3. Right, whereas here it is 1, 2 position. This is called right. So this group is imidazole, and this group is called indazole. Okay, indazole. So very similar, RuCl4 2-, RuCl4 moiety, and then we have 2 nitrogen donuts like here. So here we have 2 imidazole moiety, here we have 2 benz indazole moiety, and again the outside here we have a cation. So these 3 ruthenium compounds are now at very active stage of trial, I mean third phase of clinical trial, and some of them has already been actually in some countries they have been allowed for treatment protocol for the cancer chemotherapy. The advantage of the ruthenium complexes is there much less toxicity, and moreover these ruthenium complexes are very good. Some of these ruthenium complexes are very good for the treatment of leukemia, certain kinds of leukemia, and sorry, and again colon and rectal cancer, for which platinum complexes are not so much active. And also probably some of you may know that in cancer there are 2 kinds of growths. One is called the primary cancers, I have already discussed probably, and the other is called secondary cancer cells or metastasis, where metastasis, as I have told you previously in this slide, that sometimes some cancer cells can break off from the original tumors and travel to some distant places through blood or lymph, creating metastasis. This metastasis, I have told you, is more dangerous than the normal cancer cell. Now it is found that a combination chemotherapy using platinum complex and one of these ruthenium complex, particularly NAMI-A, is very effective, because the platinum complex attacks the primary cancer, whereas NAMI-A attacks the metastasis. So if you have a combination chemotherapy using a platinum complex like cisplatin or carboplatin and another ruthenium complex like NAMI-A, then their combination gives a very good effect on both the primary cancer and the metastasis. So these are coming as new protocols for cancer chemotherapy. And for academic interest, I have discussed here some more ruthenium
Hello, sir.
complexes, but you may not. Yes.
Hello, sir. Sir, how this compound
Yes.
differentiate the metastasis cancer cell in our blood or limb from the other normal cell and kill them?
No, actually, I have told you that they will attack both the primary cell and both the normal cells as well as cancer cells. So people are trying to, so in a way you cannot say that they will differentiate between cancer cell and normal cell. The difference is that in cancer cells, because of high metabolic activity, there is more blood flow. You will find that in cancer cells, more blood flow is there. Because there is more blood flow, and because these compounds actually passes through blood, it is administered intravenously. So if you have some cells where there is more blood flow, obviously more amount of compound will be delivered at the cancer cells than at normal cells. But most of the complexes cannot distinguish between normal cell and the cancer cell. But I have told you that you can design some prodrugs, right? And these prodrugs are such that though they are delivered in normal cells as well as cancer cells, in the normal cells they will remain dormant for a long time, so they will not be activated because of the lack of reduction potential, lack of electrons. On the other hand, in cancer cells, because there is more metabolic activity, and because of the hypoxic environment in the cancer cells, those prodrugs will get activated by reduction. And as a result of this, though the compound is delivered both in normal cell and cancer cells, but in the cancer cells they will show more activity, and so more cancer cells will be destroyed than the normal cells. But as of now, there is no such chemical compound which can distinguish normal cell from cancer cell. That's why any cancer chemotherapy has got serious side effect, because along with normal cells, along with cancer cells, normal cells are also destroyed, and that is the disadvantage of chemotherapy. Okay. But if you ask me how it can distinguish metastasis and normal metastasis and primary cancer, then I may say that we are not going to the deep details, because different complexes has different pharmacokinetic pathway, how they enter inside the cell, how they get activated, to which cell component they binds. They vary from one compound to other compound. So by trial and error method, now people have actually located some complexes which are more active against the primary cancers, and some complexes which are more active against metastatic cancer. So now we have a list of compounds. Doctors have a list of compounds, and so they use combination chemotherapy to attack both the primary cancer cells and the metastatic cancer cell. Okay.
Yes, sir. Understood.
So I think this will be sufficient for you. So I will not go further. Up to this point, you have the mid-semester syllabus. So wish you best of luck. By today evening or by tomorrow, I shall send you some previous year's recording of these two lectures. That means this today's lecture and the previous day's lecture, that I will share with you. Okay.
Sir, can you send this PDF?
If you have any, no, not PDF. I have told you that I am repeatedly telling you that I shall not share the PDF of these slides. I shall send you recordings of previous year's lectures.
Okay, sir.
Okay. Thank you. Wish you best of luck for the mid-semester. Just one question, because the head of the department told me that what is the progress of your physical chemistry? Do you have sufficient physical chemistry classes?
Yes, sir. Chemical kinetics, rate equation.
How many classes you have? Okay. You have sufficient. You have finished the chemical kinetics part. Okay.
Sir.
How many physical chemistry classes did you have? How many classes? Can you roughly tell me? 3 or 4?
Yes, sir. Math 5 or
Yes,
6.
sir. 4 or 5 classes, sir.
Okay. Thank you very much. Thank you.
Sir.
So if you have any question, I will stay,
Yes,
or
sir.
otherwise leave.
Yes, sir. I have a question. Which book do you recommend for the preparation of inorganic chemistry? Which
I
reference
have
book?
probably discussed this. Just let me. I have told you these two books, Ekedas Bioinorganic. This will be the best book, Ekedas Bioinorganic, for this part, okay, bioinorganic part, or RP shortcuts in organic chemistry, or you can look for any standard inorganic chemistry book and you will have some chapter on bioinorganic chemistry. But
Okay,
the
sir.
best book follow is this one, Ekedas Bioinorganic chemistry. Okay.
Sure, sir. Thank you, sir.
Okay. So I'm leaving, okay?